Hi folks, today we're going to have a look at how we can apply the quadratic equations that we've been using to solve some problems. We could problem solve with a variety of strategies, but because we've been studying quadratics, let's use them in these three questions. So the first one is a rectangular sandpit is 2 meters longer than it is wide. If it occupies an area of 48 meters squared, determine the dimensions of the sandpit by solving a suitable equation. So if we don't use some kind of algebra in here, we actually haven't answered the question because it tells us we have to solve a suitable equation. So if you only used guess and check, you wouldn't get any marks on a test. Let's pick out some other key information here. We know that it's a rectangular sandpit. So let's actually start with that. Let's draw ourselves a diagram. Let's make it a rectangle. That makes sense. There we go. There's my rectangle. And it's 2 meters longer than it is wide. So we don't know how wide it is. So let's make the width of the rectangle equal x. Why do I do that? Well, I've got to create an equation. Let's bring in a variable. So the width is x and it's 2 meters longer. So the length would be x plus 2. And I also know that it has an area of 48 meters squared. 48 meters squared. Cool. Determine the dimensions. So what we've got to think about is, well, how do we connect this information? We know that it's got the length and the width and the area. And we also know that we can find the area of a rectangle by doing the length times the width. So let's use, oops, sorry, pressing the wrong buttons there. Let's use this formula to set up our suitable equation. All right, let's have a look at what that looks like. So if we know that area equals the length times the width, then we can say that 48, the area, is equal to the length times by the width. The length times by the width. Okay, first algebra quadratic technique we've learnt is expanding. So let's expand that bracket. And we've got to find the dimensions of the rectangle. So what that's telling me is that we need to find the x value. So in maths terms, what does that mean? It means solve for x. And how do we solve a quadratic equation? We use the null factor law. Now my problem at the moment is I don't have a null. So let's actually start this off by getting a 0 on the left hand side. And now I have my null. The next thing I've got to do is get my factors. So what am I going to do? I'm going to factorize. Of course I'm going to factorize. Now I know this is a monic trinomial, so I can jump ahead the first couple of steps of our factorizing process, and I'm going to look for two numbers that multiply to equal negative 48, and I need the same two numbers to add to equal positive 2. Right, so let's go through our factors of 48. We could have 12 times 4. Now they're not going to go together to get 2. I could have 6 times 8. They absolutely can go together to get a 2. And what I'm going to do is I'm going to say, well, let's do 6 times 8, 6 times 8. Now one of them is going to have to be a negative to get negative 48, and because I have a positive 2, let's make the smaller value the negative 1. Okay, so this can be factorized into x minus 6, x plus 8. And to solve this, well, if x minus 6 equals 0, then x equals 6. And if x plus 8 equals 0, then x equals negative 8. Now let's think about that logically. We've got two answers. X can be 6 or x can be negative 8. They both solve the quadratic equation problem. But they don't make sense for a rectangle. How do you have a side length of negative 8? Doesn't work. So we're going to take just this one and we're going to cancel them out, say can't be. And it's a good idea to always state why you're getting rid of a value rather than just cutting it out. Quick little sentence to say can't be a negative length. So here is my x value. All right, have we actually answered the question? Determine the dimensions of the sandpit. All we've done is said what x is. So we now need to actually answer the question. Now if x is equal to 6, then the width, remember we said let's make the width x. So the width is 6 and the length is 2 meters bigger. So it will be 8. And we've finished the question. That's it. So we've used a quadratic formula. We have thrown in some expansion. We have thrown in some factorising. And we've thrown in some solving. And applied it to a area problem. Nice. Let's have a look at another one. This is a classic problem that I remember getting when I was in primary school. We have the product of two consecutive numbers is 72. So product, let's actually highlight some of our key information. Product means times. Two consecutive numbers is 72. All right, so that two consecutive numbers, that means two numbers that come one after the other, equals 72. Again, we can't just use problem solving techniques and guess and check because it tells us to use a quadratic equation. If we don't use a quadratic equation, then we're not answering the question that we've been asked. All right, so let's set this up, the product. So I multiply two numbers together. So let the first number equal x. So then the second number, now if they're consecutive, that means one number comes after the other. So the second number would equal x plus 1. And we know the product of these two numbers is equal to 72. And you can see I've created almost an identical problem to the previous example. So I'm just going to run through this quickly. I'm going to expand it first. And then if I'm going to solve this problem, I need to use the null factor law. So before I can use the null factor law, I need to get null. Remember, null is just another way of saying 0. And it's the null factor law, so I have to get factors. Again, it's a monic trinomial. So I'm looking for two numbers that multiply to equal negative 72. And the same two numbers that add to give 1. Now, two consecutive numbers, we're assuming that they're going to be whole numbers in this situation. So let's see what we can come up with. Multiples of 72 that might add together to get 1. Right, what could we do? What can we get 72 with? We could have 12 times 6, but they're not going to go together to get 72. We could have 72 times 1. They're obviously not going to go together to have a difference of 1. So I've got to think about numbers that are sort of like separated, have a difference by 1. And they are, hopefully you've thought about it already, 8 times 9. Okay, so I'm going to put my 8 in here, my 9 in here. Now one of these numbers has to be negative to get a negative 72, and they also have to get a positive 1. So if it's a negative 72, one of them's negative. Positive overall, we need the smaller number to be the negative 1. So it's going to be negative 8 times 9. And now we can factorise to x minus 8 x plus 9 equals 0. And using our null factor law, if x minus 8 equals 0, then x equals 8. And if x plus 9 equals 0, x equals minus 9. Okay, so let's think about, have we actually answered the question? Two consecutive numbers multiply to equal 0. To equal 72. And in this case, there's no reason why it can't be negative 9. Negative 9's a number. The question doesn't say anything about it having to be positive. It's not a length. So let's actually say if x did equal negative 9, then the next number would be negative 9 plus 1. Alright, so my two numbers. So two numbers could be negative 9 and negative 8. Okay, those two numbers are consecutive and they multiply to equal 72. Or, that doesn't say or, that says of. Or, if x equals 8, then the next number, yep, you've guessed it already, 8 plus 1, the next number's 9. So the two numbers could be 8 and 9. Now the question actually gave us a hint here. If we read it carefully, find the two sets of numbers. So if we stopped with one set, we haven't actually answered the question we were asked. So always make sure you read the question carefully and pick out that key information to help you along the way. The final example I want to run through is a little bit different. So this is where we get to start and apply our knowledge to an application where we've got some things happening in real life. We're not really problem solving here. We're looking at the equation and we're finding some key points that might help us. So a cable for a suspension bridge is modelled by the equation 1 over 800 times by x minus 200 all squared plus 300. So we're starting to get some big numbers here. Maybe we're going to break out a calculator to help us. All right, so what is this cable for a suspension bridge? So we need to draw a diagram to help us visualize what's going on here. Now, if you don't know what a suspension bridge is, that's one of the bridges that goes like this. Okay. So when they talk about the cable for the suspension bridge, they're probably talking about this cable in this space right here. Why? Because I know that this is a quadratic equation and this cable here looks like a quadratic. Okay, determine the turning point of the graph of the equation. So if we were going to graph this, because it's a quadratic, it's going to have a turning point. And from my graph here, we can see that that point would be right there. And my equation is in turning point form. So I know that the turning point has moved 200 places. Now, move, translate's probably the correct word we should use. Translated 200 places right, and translated up 30 places. So that means my coordinates here is going to be 230. And that is my answer to part A. Done. I hate when students write their answers next to the question like this, but because I'm working in a video, it's just easier to keep everything on the same page for as long as possible. Okay, if the bridge is symmetrical, quadratic equations are always symmetrical, so we're going to assume that the bridge is symmetrical. Determine the suitable values of x. Okay, so my bridge is symmetrical. Determine the suitable values for x. How could we possibly do this? So let's think about what values will actually work for x in this problem. Well, we could have some kind of bridge. Is it going to go on forever? What do I mean by is it going to go on forever? Well, we know that the bridge is symmetrical, so it could be something like this when I put it on a graph. Now, if this is my x-axis and my y-axis, then I'm going to actually assume that my bridge is going to go from this point to some other equivalent point on the other side. Now, I know that this is going to be 230 in the middle. Now, there's nothing to say that I couldn't make the bridge go further out here, but I'm just going to use the assumption that, let's say that the y-axis is going to be one of the pillars of my bridge, and we're going to use that as my suitable x values. So let's actually find out what the y value is when x equals 0. And I think I'm actually going to probably answer a future question here, but let's just, not quite what it's asking, but think about this logically. If x equals 0, then y will equal 1 over 800, lost my equation now, x minus 200 squared plus 30. So that would be 1 over 800 times by 40,000. How did I get the 40,000? I just did, made that a 0. 0 take away 200 is 200, and 200 squared is 40,000, plus 30. So 40,000 divided by 800 plus 30. Yes, these numbers are big, but we can use our simplifying skills to cancel it down. 400, how many 8s? That's going to be 50, plus 30, which equals 80 meters. So we've got this point here, when x is 0, y is 80. So logically, this point over here is going to be something 80 as well. And I don't need to do any fancy maths. It tells us that the bridge is symmetrical. So if the distance from the center to the top is on the left, from the center to the top on the left hand side is 30 meters, and the distance on the right hand side would also be 30 meters, making this 60. So I went off on a little bit of a tangent there, but I was thinking about suitable values for x. So we could say that the suitable values for x are 0 to 60. Now, how do we write that formally? We say let x be greater than or equal to 0, less than or equal to 60. All right, part C, determine the range of values of h. So as I mentioned, I'm probably going to answer a future question. And when I found out that we have these points at 80 and 60, 80, what I've actually done is found the range. The range is all of the possible y values. So my possible x values, that's called the domain of the graph. And the y values, that's called the range. So my y values go from 0 to 80, and that's called the range of the graph. Okay, next D. Sketch a graph of the equation for the suitable values of x. Again, we've actually done that. So all of our thinking that we did around B has answered some of those future questions. I'm just not happy with that graph. I want to do a slightly better one. So I'm going to redraw my axes. Now it's a sketch graph. It doesn't have to be perfect. It should be roughly symmetrical. So I'm going to use my grid lines to help with my symmetry. I'm going to put in some key points here. And I'm going to draw my graph. Best graphs always have the key points listed as coordinates. So this is the point where x is 60 and y is 80. And this is the point where x is 0 and y is 80. And this is 30. I've got a feeling I've got that wrong now, haven't I? Oops, I've just made a mistake. Big mistake, actually. That was 230. So then that means that one has to be not 60, but 400, because the distance was 200 and 200. But because this video has been going for so long, I'm not going to restart and correct that mistake. I'm just going to go back and fix my answers here. So that should have been not 200. 200 was the midway point. That should have been 400. This point does not change. Okay, it's still the same because that was the height. Now in my graph, the other thing as well, because these are endpoints and it goes right up to that point and includes it, then I have a closed dot at those points. It's important to actually draw those dots to mark the endpoints. Okay, that's the graph. Sketch done. What horizontal distance does the cable span? So now we're actually just trying to interpret what's happening here. So the horizontal distance is right there, and that's my suitable x values. So the horizontal distance is 400 meters. 400 meters. What is the closest distance of the cable from the base of the bridge? Again, interpretation. Here's my graph, here's my bridge. So that's the bridge, that's the bridge. The closest it gets is 30 meters. Again, we're interpreting what this information actually means. And what is the greatest distance of the cable from the base of the bridge? Again, my greatest distance, interpreting our information. Largest distance from the base of the bridge, 80 meters. 80 meters. So I made a little bit of a mistake there, but I kind of redeemed myself at the end. Hopefully that wasn't too confusing. Remember to ask some questions in class if you get confused.